Hello, my name is Jonah Wu, and this is my Physics 2211 Lab 2 Motion of a Falling Object. The purpose of this lab was to observe the motion of an object that is dropped from rest at a small height above the ground and falls somewhat slowly. For this experiment, I dropped a crumpled up paper ball from a small distance above the ground and tracked it in the tracker software. For this experiment, we created two basic models. One was a model with no air resistance, and one was a model including the drag force, which was basically air resistance. The main fundamental principle involved in this lab was Newton's second law, or the momentum principle, which states that the net force on an object is equal to the change in momentum over the change in time. From this, we can derive the velocity update formula shown to the right, and also the position update formula shown to the right as well. For constant force, in the case of only gravitational force, the average velocity can be considered to be 1/2 times the initial velocity plus the final velocity. Additional fundamental principles include the gravitational force near the Earth's surface, which is negative mg in the y direction, and the gravitational constant g can be derived by using the formula for gravitational force, and it is approximately equal to 9.8 meters per second squared. The gravitational force near Earth's surface points downward during free fall motion. Additionally, we consider the drag force, which is the force opposite of the direction of motion due to the air resistance. This is proportional to the square of the object's speed and will point upwards in freefall motion, as shown to the right. Here's a video of the tracker analysis of the falling paper ball. Here is the glow script computational model that I included. Take note of the initial conditions, the drag constant with and without consideration, and the net force calculation. As you can see here, we initialize the system with a mass of 0.005 kilograms, 0 initial position and 0 initial velocity. Time steps are here. The gravitational constant of 9.8 meters per second and the positive y direction pointing in the positive y direction. Here is the drag constant, which is 0.0105. However, when it is equal to 0, the model is gravitation only, and there is no air resistance. However, when it is greater than 0, the drag force is present. Here we can see the calculations of the net forces. Fg is equal to negative mg in the y direction, and drag force is equal to b times velocity squared in the positive y direction. And Fnet is just the sum of those two forces. Here is the program itself. For this experiment, we define our system to be the paper ball. The surroundings of the system are the earth and the ground, and as seen as in the glow script code, our initial conditions are a mass of 0.005 kilograms, position at the origin, of velocity equal to 0. Note that the drag constant here was purely experimental. Here is a graph of the actual versus the predicted motion with and without drag force. All three of these motion curves, as you can see, model an object in freefall motion dropped from a certain height. In all of these cases, Fnet is not equal to 0, as the object's velocity is changing. However, the theoretical model without the drag force significantly deviates from the model with drag force and the actual model of motion. There are even slight differences even among actual motion and the model of motion with drag. Which models, if any, predict a terminal velocity? The top model shows the model with no drag force, aka b equals 0, and therefore there is constant acceleration. The bottom model includes drag force, and it shows velocity approaching a terminal velocity. This is because drag force balances out gravitational force at a certain point during the object's motion. So therefore, the net force acting upon the object is equal to 0, so the change in momentum is equal to 0, and therefore the change in velocity is equal to 0. What if the object was initially thrown downwards? As shown in this model, it was thrown initially downwards with initial velocity 0, -2, 0 meters per second. However, the object still approaches the same terminal velocity. It only takes less time to reach this terminal velocity. There are several possible sources of error within this experiment. The first was slight differences in tracking the center of mass of the paper ball in the tracker software, and this will affect the position tracking and cause discrepancies in the graph of the ball's motion. Another possible source of error was that the object is not completely stationary during free fall, and it does not fall completely in a straight line. The paper ball rotates a little during motion, and this will affect position tracking by generating small unknown forces that are not accounted for. Finally, there is the inaccuracy of the drag constant, which was purely found by estimation and may not accurately model the actual drag force on the paper ball.